Hi, folks, it's Mr. V, and today we're looking at illustrative mathematics, which is our text in Congruence, Unit 2. We're going to be talking about the side-side-side triangle congruence theorem. So far, we've talked about the side-angle side, where you have the two sides of the triangle and the included angle. We've talked about the angle-side-angle theorem, triangle congruence theorem, where you have two angles that are congruent and the included side, the side that's between them, are congruent. Today we're talking about the side-side-side. And by the end of the lesson, you should be able to say, I can explain why the side-side-side triangle congruence theorem works, and I can use it in a proof. We will do both of those today. So first we have to create a triangle with the given side lengths. And you move these around, you get to try to move them to where they match up. And sometimes it's easier, sometimes it's hard to try to get to be exactly at 4. I don't know. Maybe I'm just going to settle for 4.01 or something. So you try to make this be the same. And then I'm going to try to get it to be 7 and to be 8. So let's see, 8 is about right here. And this is pretty darn close. It's not exactly right, but it's close. And the question is, can you make a triangle with these properties that doesn't look like somebody else's? The answer is no, you can't. Well, do you think that we'll be able to prove, if all that we know about a pair of triangles is that the pair of corresponding sides are congruent, that we'll be able to prove, to use transformations to take one onto the other to prove that all of the vertices coincide? Yes, that's what we're trying to do today. It's called the side-side-side triangle congruence theorem. So the first thing we're going to do is to try to create a sequence of rigid motions that takes SUT onto GHJ. And when we do this, we will first of all create a transformation. Let's see, here's one, translate. This is the one that translates from S to G. And if I apply that to this triangle, there it moves it. And I'll change the color of this so that you can see that this is my translated. This is now S prime, U prime, T prime. I can also rotate it. So if I rotate it, and I rotate it by how many degrees? Well, let's just check it, make sure that this degrees that's listed is correct. I'm going from this angle to, I'm going to rotate it this much. There's 54 degrees in the clockwise position. So it's going to be a negative 54 degrees, which is this one. And if I apply that transformation to this triangle, there we go. And again, I'll change the color so that you can see that this is a different triangle. There we go. And now we reflect it. And I've actually defined the reflection here across GH. When we apply this, you can see that the two triangles line up. If two triangles are congruent, you can always map the one onto the other with a translation, rotation, and reflection. You may not need all three, but if you do, one reflection, one rotation, and one translation will get you on top of the other. That's pretty cool to think about. So we're going to prove it here. It says here, this proof, two triangles are congruent if three pairs of corresponding sides are congruent. Side, 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 triangle congruence theorem. We're going to use a new line of argument. Now this is important. 2 points coincide if, after reflection, they're the endpoints of a segment that is perpendicularly bisected by the line of reflection. This is what we talked about yesterday with the perpendicular bisector theorem. If you have the line of reflection, and a point is, that line of reflection is going to be the perpendicular bisector of the segment when you reflect across it. And notice we don't have any angles when reducing the side, side, side. So we're going to try to do this same kind of thing as before, only we're talking about it differently than we did when we had rays. So here is a proof, and you're to fill this out. It says segment ST is congruent to segment, segment GH. So they're congruent. Therefore, there's a rigid motion that takes ST to GH. Apply this rigid motion to triangle STU. The image of T will correspond with H. The image of S will correspond with G. And we can't be sure yet that the image of U, which we'll call U prime, so if I were to draw this on here, it would look something like this. And this is what you should be doing as you're going through it. You can draw on here. You can say, this is going to be S, this is going to be T, and this would be u prime, we can't be sure that it lines up with j just yet. If it does, our rigid motion takes STU to GHJ, proving that triangle STU is congruent to triangle GHJ. If it does not, well, then you continue as follows. Oh, let's see. We cannot be sure that it coincides with J. We want to make sure that it coincides with J. By the way, folks, this is a rigorous proof. I'm not asking you to do it, but I want you to understand it, so I want you to be able to fill in the blanks. So you should try to do this on your own. Let's see. HJ corresponds with U prime T, or TU prime, because rigid motions preserve distance. Therefore, H is equidistant from U prime, and H and U prime are the same distance. H is equidistant from U prime and J. Oh, the singular argument shows that G is equidistant from U prime and J. GH, which is right here, is the blank of the segment that joins U prime and J prime. It's the perpendicular bisector. And because the perpendicular bisector is determined by 2 points that are equidistant from, so since this is the same distance here, and this over here is the same distance as this one, these 2 points are equidistant from these endpoints. That makes this on the perpendicular bisector. This is on the perpendicular bisector. When you draw this line, this is the perpendicular bisector. The reflection across the perpendicular bisector of U prime J, takes U prime to J. Therefore, after the reflection, all three pairs of vertices coincide, proving triangles, we're going to say STU, and GHJ are congruent. And there you have it. And if you want to, you can check my answers on the next page with yours. The goal of this discussion was to come to a consensus on the summary of Prior's proof. Prior used rigid motions to line up the segments, just like before. So we said two segments, if they have the same length, they are congruent. So there's a rigid motion transformation that moves one to the other. So she didn't start with one point and then rotate. She just said, well, let's just do whatever it is that gets those two together. She defined a perpendicular bisector and then reflected over the perpendicular bisector of the line to the line of the third vertex. Each pair of corresponding sides is used in the proof, and there's no angles that we used. So using perpendicular bisectors is a new reason why vertices have to coincide. Cool. Now here's a link. This link will take you to some sentence frames that you can use in proofs. And you can use this sentence frames, and you can use your reference chart on a test. So you might want to make a copy of this and put it in a safe place, like where you have your reference chart. Make sure you add this to your reference chart, the side, 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 triangle congruence theorem. In two triangles, if all three pairs of corresponding sides are congruent, then the triangles must be congruent. Side, 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 triangle congruence theorem. What else do we know for sure about parallelograms? So the goal for this activity is to prove that the opposite angles of a parallelogram are congruent. A parallelogram, and we're going to use the shortcuts that we have already discussed. So for example, in this parallelogram by definition is a quadrilateral with both pair of opposite sides parallel. And that's what we've got here. That's what's been given here. So I'm going to mark this, and you can watch this proof. I'm going to use one of the shortcuts. I think I'll use the angle side angle proof. I could use other ones, but I'm going to use the angle side angle triangle congruence theorem to do this one. And you watch how I use this shortcut, which we've proved. We've proved the shortcut, so I don't have to prove it again. All I have to do is to show that these two triangles are congruent. So the first thing I do is I say if I have these two lines that are parallel like this, and my transversal goes this way, then that would mean that these alternate interior angles are congruent. So I'm going to mark these alternate. And I could label them BCA and DAC, but I'm just going to label them angles 1 and angle 2. So I'm going to say step 1, angle 1 is congruent to angle 2. Why? Well, they're alternate interior angles formed by transversal crossing parallel lines. Alternate interior angles are congruent. That's the alternate interior angles theorem. And it's true because these two lines are parallel. So I can say because BC is parallel to segment AD. It's not because AB and these two are parallel, it's because these are parallel. And this is an angle for both of these. So I'll circle it. The second thing we're going to do, if we're going to use the angle side angle, we'll choose this side. Segment AC is congruent to segment, and I'm going to label it CA, but it's the same segment, so you know that. I'm labeling it so that when we go around it, we'll go around this way for the one triangle, this way for the other. But what's my reason? Well, it's a common side. It's the same side, and it's the reflexive property. Now, do I expect you to use that? If you don't remember the word reflexive and reflexive property, you can just tell me it's a common side when you tell me why, what your reason is. There is no shortcut angle side. I need another angle. Well, here we have an angle. This would be angle side. I would need to know this angle and this angle. And are those congruent? Is angle 3 congruent to angle 4? Well, yes, it is. Why? Because when I have these parallel lines in this transversal, the alternate interior angles formed here are congruent to the alternate interior angles formed here, just like I've marked. And it's because these sides are parallel, not because AB and AD and BC are parallel. It's because they, well, let's just write it out. Angle 3 is congruent to angle 4. Angle 4. Because they're alternate interior angles that are congruent, formed by AB being parallel to DC. Notice these parallel lines are not the same as these. I've drawn my picture so you can see it. And this is a set of angles. So now we have the angle side angle, angle side angle, angle side angle. So I can say in step 4 that triangle, and I'll use 1 tick, 2 ticks, no ticks. That's ACD is congruent to 1 tick, 2 ticks, no ticks. This is CAB by the angle side angle, triangle congruence theorem. So we used a shortcut to prove that the two triangles are congruent. I only used 3 parts of these two congruent triangles. After using those 3 parts, I can say that all of the remaining parts, if 2 triangles are congruent, all of their corresponding parts must be congruent. So all of the remaining corresponding parts of the congruent triangles are congruent, CP, CTC, which means that angle B is congruent to angle D. And that's what we tried to prove. The opposite angles in a parallelogram are congruent. Done. We could have done this. I'm not going to write it out, but I'll show you. We could have done this using the side angle side triangle congruence theorem. I could have said, well, in a parallelogram, we have proved earlier that the opposite sides have to be congruent. Also, since these lines are parallel like this, no, I don't want to use that. I'll use this. Since my lines are parallel like this, my alternate interior angles are congruent. So this angle must be congruent to this one. And this side is congruent to itself by the reflexive property. By the side angle side triangle congruence theorem, the two triangles are congruent. Since they are congruent by CP/CTC, the remaining parts have to be congruent. Angle B is congruent to angle D. Further, I could have said, in a parallelogram, we previously proved, parallelogram by definition is that both pair of opposite sides are parallel. It doesn't say anything about the side lengths, but we've proved that the opposite sides are congruent. So I could use that theorem in proof. These two sides must be congruent. These two sides must be congruent. And this side must be congruent to itself. So by the side triangle congruence theorem, the two triangles are congruent. And since they are congruent, using the shortcut, using only 3 of those 6 parts, since they are congruent, all the remaining corresponding parts of congruent triangles are congruent. CP, CTC, corresponding parts of congruent triangles are congruent. So angle D is congruent to angle B. This is pretty cool. What it means is that in a parallelogram, opposite angles are congruent. That's not a definition. The definition is that opposite sides, both pair of opposite sides are parallel. But we've used that to prove that both pair of opposite sides are congruent. And now we're proving that both pair of opposite angles are congruent. I wonder what else we can prove about parallelograms. We'll see. Maybe we'll think of something else. So in the cool down, you have practice seeing what's going on. But before we do that, let's look at this right here. So far, you've learned the angle-side angle, the side-angle-side, triangle congruence theorems. Sometimes we don't have enough information. In this case, we have the side-side-side triangle congruence theorem. So to prove two triangles are congruent, look at the diagram, look at the information that's given, look at information that might be implied to see whether you can tell whether the triangles are congruent. And then if they match up one of your shortcuts, use the shortcut to prove they are congruent. So here we have three triangles, and you get to choose which one works, if any. And spoiler alert, I'm going to show you what these answers are before we go on, and we will continue this. So in a circle, I know that the sides of a circle, radii of a circle are congruent, so I'll mark these two are congruent. And since a segment is congruent to itself, here we have the side-side-side. This is what I would use to show these two triangles are congruent. In this second one, we have one side here. We have one side here. We have an angle here. We have an angle here. And we have a side here that's congruent to itself. So we have a side, we have a side. And some people think that this is the side angle side. But notice, between the two congruent sides, I do not have the included angle. The included angle would be here and here. We don't have that. What we have is ASS, or SSA, the donkey theorem. And it works sometimes. Is this one of those times? We don't know. We haven't talked about it yet. So this is none of the above. Beware. Once again, we have a circle. Radii of a circle are congruent. That's one of the very first things that we learned. We also have a segment that's congruent to itself. Oh, look, side angle side. This is by the side angle side shortcut. I can show that these two triangles are congruent. These radii were not marked initially. This segment that's congruent to itself was not marked initially. It's implied, but it's something that you have to determine by and you have to give a rule. If you were going to be doing this in a proof, you would say, well, these are radii of a circle. Radii of a circle are congruent. So you have to have a rule before you mark something on a drawing. Don't just mark everything and think that you're right. You have to, before you mark anything, you better have a rule to mark it. So good luck and success.